Assalamualaikum warahmatullahi wabarakatuh. So in this video, I'm going to give another classic example related to the application of integration in physics. So in this video, we are going to look at the idea of work and in everyday language, it is just the total amount of effort required to perform a task. When it comes to physics, however, it has a technical meaning that depends on the idea of force. So, force describes either a push or a pull of an object. As an example, you can have a horizontal push of a book across a table, or you might have a downward pull of Earth's gravity on a ball. Now, if we relate this idea of work and force with what you have seen in the previous video, with the scenario of an object that moves along a straight line where it has the position function described as st. So this is the position function. Then the force on the object in the same direction is given by the Newton's second law of motion, which is this one. This is the mathematical equation where the force is equal to m times with the second derivative of this position function here. So notice that this second derivative is actually is just acceleration a, so therefore force is equal to m times a. In the SI metric system, mass will be expressed using the kilogram unit. So you have mass in kilograms, displacement in meters, time in seconds, and the unit of force will be in newtons, where newton is equal to kilogram meter per second, and this can be clearly seen based on this equation here, because mass is in kilograms, so you have kilogram over here, and this is acceleration, which is meter per second. When it comes to another system, which is the US system, the unit of force that is used is pound. Now, when acceleration is constant, so this is the case when acceleration is constant, you can find the work done using this simple formula, which is force times the distance. Now, there are two different units related to work. So if you consider the SI metric system, then F will be measured in newtons and D in meters. Therefore, the unit for the work done is Newton meter, or it can be simply expressed as joule, which can be represented by alphabet J. Now, if you consider the US system, therefore F will be measured in pounds and the distance will be measured in feet. Then the unit for the work done here is foot-pound, which can be represented as using this. This is for foot, FT is foot, and this one is representing the unit pound. Okay. Right, now we are going to look at a simple example related to what you have seen in the previous slide. So in this example, it is asking you to find how much work is done in lifting a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meter high. So we are going to consider 1.2 kilograms. So this is the mass, and the acceleration here is going to be the gravity, which is 9.8 meter per second. So before we can find how much work is done, we need to first consider what is the force in this given scenario here, and the force is m times a, and in this case m times with the gravity. So the mass is in kilogram, and it is 1.2, and the gravity is meter per second, which is 9.8, and therefore our F is 11.76 Newton. And using this result, we can then find the work. So work is force times with the distance. So the distance is 0.7 meter. You are moving the book from the ground, from the floor, up to 0.7 meter high. So force is 11.76 times with the distance, which is in meter, 0.7. And since the unit is in Newton and meter, the work will be equal to 8.2. The unit is going to be in joule, so 8.2 joule. Okay, so this is for the first question. Next, for the second question, we're going to look at how much work is done in lifting a 20-pound weight 6 feet off the ground. So in this case, force is already given as 20 pounds. So this is the US metric system. So force is in pounds, 20 pounds, and therefore the work done is F times D. So 20 pounds times 6 feet. So the distance is in 6 feet. The unit is feet, therefore this becomes 120 foot-pound. So the unit is foot-pound. Okay. Alright, now the previous example that you have seen is all related to the force being a constant value. Now we are going to look at the scenario where the force is not constant. And when this is not constant, the work done in moving the object from point A to B can be found by finding the integral of the function fx here. So f here will represent the force. Okay, so this is the force. So you can find the integral of this function from point A to B. We are going to look at the first example here related to the scenario where the force is not constant. So in this example, a particle is located at a distance which is x feet from the origin. So notice that the distance unit is in feet, so you're talking about the US system. A force of x squared plus 2x pounds x on it. So this is the force, and the force is in pounds. The unit is in pounds. Again, this is US system. So how much work is done in moving it from x equals to 1 feet to x equals to 3 feet? So because of that, the work, the unit of work will be in foot-pound. Okay. Alright, so since the force here is not a constant, you can see that this is a function that depends on x. What is x? X is the distance from the origin. So therefore the work done can be obtained by finding the integral of this function here, which is x squared plus 2x dx, where the limit is from 1 to 3. This is a straightforward function where you can evaluate it quite easily. You will get x cubed over 3 plus 2x squared over 2 will be evaluated at 0.3 and 1. 2 over here can be cancelled out. So therefore we have 3 to the power of 3. So over 3 plus 3 squared minus 1 of 3 over 3 plus 1 squared, and this is just going to be 27 over 3 plus 9 minus, this is 1 over 3 plus 1, so that would be 4 over 3. Okay, so you will have this one, you will have 18 minus 4 over 3, and that is equal to 50 over 3, where the unit is going to be foot-pound. Okay. Alright, that's all for now. Thank you very much for watching, and I will see you in the next video.